All right, so this section is going to go over springs. So, similar to how masses store kinetic energy, springs store potential energy. And like velocity for a mass, a spring is described by deflection, or deformation, or even sometimes displacement. So, just about all physical objects deform. So, the idea of a spring, an elastic element, applies to many things in the world, including beams, rods, cables, and helical springs themselves. And that's how we're going to draw them in this class for the most part. So, the core equation for a spring is Hooke's law, the linear force deflection model. And what that equation says is the restoring force for a spring is equal to the spring constant K times the change in length from free length, which I'm going to represent by X or either D. Actually, D in a lot of this class. So we're looking at specifically for ideal springs in this case. And let's go through a few examples. So let's start out on the left here. So we have a spring connected to a wall. It has some free length L. And then if we're going to move the spring to the right here, our deformation or deflection is going to increase, making this D is greater than 0 if we spread the spring out. On the other hand, if we take this point and push it inward, we're going to get D is less than 0. So we're compressing the spring in this case. Now, if we look on the right side, we start out with a spring that's not connected to any walls whatsoever. And it's starting out at its free length where D is going to be equal to 0 for that case when the spring is at length L. If we take one side and compress it by an amount A, our deflection is going to be negative A. If we take the other side and compress it that other direction, we're also going to get a deformation of negative A. And if we take those 2 points and spread them out by an amount A and B, our deformation is going to be equal to A plus B. And if we finally take these points and just shift them over both by the same direction and amount A, we're going to get a deflection of equal to 0 because the spring length hasn't actually changed. It has no deformation. Its deflection is equal to 0 in this case. So, just like how a mass is described by mv dot is equal to the sum of our forces, a spring has a similar dynamic equation. What should go on the left and the right in that case? Well, a mass has mv dot, velocity, which relates to our mass. A spring has deflection. So deflection is to a spring what velocity is to a mass. So we should have something like d dot on the left. So what should d dot be equal to? So we know that the rate of change of deflection, d dot, should be along the lines of something that looks like velocity, because that's a rate of change of deflection. And like velocity and kinetic energy, there's a relationship between deflection and potential energy. So for now, let's say d dot is equal to v. If we multiply both sides, which are velocities now, by the spring force kd to get power, we end up with kd d dot is equal to k times d times v, which is our power in. And if we integrate over time to get our total change of energy, we get 1/2 kd squared. And that is our potential energy, PE, for a linear spring. Now, just a few more concepts about springs. So if we have springs in parallel, they have the same amount of deflection. So for example here, let's just ignore gravity for this case. And actually, it doesn't matter if we ignore gravity or not. So it's okay to include it. If we have our mass, which has some force applied to it and has 3 springs that are all connected essentially to the same points, well, we can draw this out as mv dot is equal to F minus K1 plus K2 plus K3, or an equivalent K equivalent here. So we can redraw the system as a mass with a K equivalent, and all we need to do to figure out that K equivalent for springs in parallel is to sum all the individual spring constants together. So in this case, we have n is equal to 3, and we would just add K1 plus K2 plus K3 to get that equivalent spring. Now for springs in series, they produce the same amount of force. So if we have a mass with 2 springs connected in a series sense underneath it, and we're going to ignore gravity for this case, we'll have a total deflection D for this case. And the way that we figure out what our equivalent K is, if we wanted to combine those 2 springs together, it would be equal to 1 over K equivalent, which is equal to 1 over the summation of 1 over our spring constant. So it'd be 1 over K1 plus 1 over K2 is equal to 1 over K equivalent. And that is going to cover springs.